In this video, I'm going to talk about unsupervised learning. You have already heard a bit at the first lecture of this course about unsupervised learning. Unsupervised learning deals with the problems in which data doesn't have labels, and sometimes that property could be problematic in some applications. The absence of labels representing the desired behavior of your model means the absence of solid reference point to judge the quality of the uh, model that you have already built. Uh, what I'm going to do in this lecture, I'm going to talk about clustering as one of the uh, possible unsupervised learning methods, and that is uh, an approach that allows building models that can be evaluated based on the data as opposed to the human judgment. Clustering is a problem of learning to assign a label to examples by leveraging an unlabeled dataset. Because the dataset is completely unlabeled, deciding on whether the learned model is optimal is much more complicated than in supervised learning. There are a variety of clustering algorithms, and unfortunately, it's hard to tell which one is better in quality for your dataset. Usually, the performance of each algorithm depends on the known properties of the probability distribution that the data was drawn from. So here I'm going to give you most useful and widely used clustering algorithms, and the first one you have already heard about, that is k-means. The k-means clustering algorithm works like this. First, you choose k, which is the number of your clusters. Then you randomly put k feature vectors called centroids to the feature space. Then we compute the distance from each example to the centroid using some metrics. It could be Euclidean distance. And after that, we assign the closest centroid to each example. Somehow you could think about it if the centroid's ID are the labels, and then we are basically assigning labels to each example. For each centroid, we calculate the average feature vector of the examples labeled with it, and these average feature vectors becomes the new location of the centroid. So for now, put it simply, we choose K clustered, we choose K centroids as well. We put the closest examples to the centroid next to the centroid, and then within that number of examples we found the middle point and we put that as the new centroid. We then recompute the distance from each example to each centroid, modify the assignment, and basically repeat this process again and again and again until the centroid locations won't change anymore. And you should remember that the initial position of the centroids influence the final position. So two different runs of k-means can result in two different models. Some variant of k-means compute the initial position centroid based on some properties of the dataset. In this picture here, you can see one run of the k-mean algorithm. The circles are two-dimensional uh, feature vectors, and the squares, if you can see, like this, uh, are moving centroids. Different background color represent regions in which all points belong to the same cluster, so it kind of represents a cluster. And the value of k, the number of clusters, is a hyperparameter that has to be tuned by the data analyst. There are some techniques for selecting k, uh, but none of them really is proven optimal. Most of these techniques require the analyst to make an educated guess by looking at some metrics or by examining cluster assignment visually. I'm going to talk about that a bit later, how to choose the number of clusters as well. While k-means and similar algorithms are centroid based, DBSCAN is a density based clustering algorithm. Instead of guessing how many clusters you need, by using DBSCAN, you define two parameters, epsilon and n. You start by picking an example X from your dataset at random and assign it to cluster 1. Then you count how many examples have the distance from X less than or equal to epsilon. If this quantity is greater than or equal to n, then you put all these epsilon neighbors to the same cluster 1. You then examine each member of cluster 1 and find their respective epsilon neighbors. If some member of cluster 1 has n or more epsilon neighbors, you expand cluster 1 by putting those epsilon neighbor in the cluster as well. And you continue expanding this cluster until there are no more examples to put it there, and then you pick from the dataset another example belonging to another cluster and put it to cluster 2, and you continue like this until all examples either belong to some cluster or marked as outliers. The advantage of DBSCAN is that it can build clusters that have an arbitrary shape, while k-means and other centroid-based algorithms create clusters that have a shape of a hypersphere. This is not the case with DBSCAN. An obvious drawback of DBSCAN is that it has two parameters, and choosing good values for them, especially for epsilon, could be challenging. Furthermore, having epsilon fixed, the clustering algorithm cannot effectively deal with the clusters of varying density. And that brings us to HDBSCAN. And it is the clustering algorithm that keeps the advantage of DBSCAN by removing the need to decide on the value of epsilon. Okay, I'm still here. Of the value of epsilon. The algorithm is capable of building clusters of varying density. HDBSCAN is an ingenious combination of multiple ideas, and describing the algorithms in full is beyond what I want to present in this course. But what you need to know from what I said is that HDBSCAN only has one important hyperparameter, and that is n, which is the minimum number of examples to put in a clusters. And this hyperparameter is somewhat relatively simple to choose by intuition. And HDBSCAN also has a very fast implementation. So, talking so much about clusters, the question that is raised is that how many clusters does our data set have? When the feature vectors are 1, 2, or 3 dimensional, you can look at the data, for example, here, and it looks like that we have 3 clusters here. But what if the dimensions are larger than 3? One of such approaches that we could use to determining the reasonable number of clusters is based on the concept called uh, prediction strengths. And the idea here is to first split the dataset into training and test set. Then run the clustering on both sets using the certain value k, which is the number of our clusters. After that, we create a co-membership matrix where of the size n test by n test, where n test is the number of observations in the test set, and the co-membership matrix is the C of X, T, R, and K is the clustering algorithm, let's say k-mean, fitted to the training dataset. We set the I primes elements of co-membership matrix to 1 if elements 1, I, and I prime of the test set fall into the same cluster, and we set it 0 otherwise. And in order to measure how well the training set centroids predict co-membership in the test set, for each pair of the test observation that are assigned to the same test cluster, a value 1 in the co-membership matrix, we determine whether they are also assigned to the same cluster based on the training centroids or not. And this is how we measure the performance. And here you can see an example of what I'm saying here. This is the full data set. We divided into training and testing data sets. And then as you can see, all the steps have been done here. Another I, I can probably go a bit more detail here. In figure A and B here, that we have done clustering for training set and test set, and each of have 4 clustering. And in figure C, we show the test example plotted over the training data and test data set. And you can see that the orange test examples don't belong anymore to the same cluster according to the clustering regions obtained from the training data set. And this will result in many zeros uh, in the co-membership matrix, which in turn is an indicator that 4 is likely not the best number of clusters. So this is a way of doing that, and you see that we need to tweak our number of clusters so that we get a better model here. There are some other approaches that I'm not going to go through. One is called gap statistics method, elbow method, and average silhouette method. And elbow method and average silhouette methods are less automatics, and some analysts use them. Okay, but we also have some other clustering methods. DPS scan and K-means compute the so-called hard clustering, in which each example belongs to only one cluster. Gaussian mixture model, or GMM, allow each example to be a member of several clusters with different membership scores. So how does GMM work? Gaussian mixture model, GMMs, assume that there are a certain number of Gaussian distributions, and each of these distributions represent a cluster, and that's why a Gaussian mixture model tend to group the data points belonging to a single distribution together. Okay, let's see with an example how GMM works. Here in this picture, we have 3 clusters that are denoted by 3 different colors, blue, green, and cyan. Let's take the data point highlighted in red. The probability of this point belonging to the blue cluster is 1 on the example on right, as you can see, and the probability of belonging to green and cyan are 0. However, next consider another point on left picture. This is somewhere between 2 different clusters. The probability of this point being part of cluster green is of course 0, and the probability that this belongs to blue and cyan is 0.2 and 0.8 respectively. Gaussian mixture model used a soft clustering technique for assigning data points to Gaussian distribution. Uh, Now you may want to know what these distributions are. So let's discuss Gaussian distribution. You probably have heard about Gaussian distributions or normal distribution, which is a bell-shaped curve with the data points symmetrically distributed around the means, as you see in this picture. Here you see a few Gaussian distribution with difference means, which is the mu, and variance, which is the delta. Remember that the higher the value of the variance, the more the values would spread. Uh, But also remember that what we said uh, is not only for single value. We could have two variable values, and instead of a 2D bell-shaped curve, we can have a 3D bell-shaped curve. Uh, I'm not going to go into details, but I just wanted to show you that this is what we call Gaussian distribution. And the values that we are used in Gaussian distributions, basically the question is how the mean and variance values of each Gaussian is assigned, are determined using a technique called expectation maximization. And expectation maximization is a statistical algorithm for finding the right model parameters. We typically use EM when the data has missing values or the data is incomplete. Uh, these missing variables are called latent variables. We consider the target or the cluster number to be unknown when we are working on unsupervised learning problem. It is difficult to determine the right model parameters due to these missing values. Think of it this way. If you knew which data point belonged to which cluster, you would easily be able to determine the mean vector and the covariance matrix. But since we don't have these values of latent variables, expectation maximization tries to use the existing data to determine the optimum values for these variables and then find the model parameters. And based on these model parameters, we go back and update the values for the latent variable and so on. Broadly speaking, expectation maximization have two steps. Uh, and ES step is basically where the available data is used to estimate or guess the value of missing variable, and in MS step, based on the estimate values generated in the ES step, the complete data is used to update the parameters. And that is exactly what is happening in the Gaussian mixture model as well. I'm not going to really go into much detail in this. I just wanted you to know that this approach exists. But for now, let's close it here and get on to do some clustering together.